Alright, that was Cold as Ice by Foreigner, as we scientific types like to call it, though. That's also known as you have an absence of heat greater than frozen H2O. Alright, I think they wanted to call it that originally, but it just didn't catch on very good. So, anyhow, here we go. Alright, we are going to start talking about the specific heat problems. Alright, I'm sure that's what everybody wants to know about. So let's just do a little refresher course first about what specific heat is. Specific heat is CP, symbol for specific heat. Don't ask me how they came up with that. But anyhow, there it is. Specific heat is CP. I guess no other combination of letters they could come up with. But anyway, specific heat has to do with how much heat energy it takes to make something change its temperature. If something has a high specific heat, that means that it takes a lot of thermal energy or heat to make the temperature increase. All right. If it also means that besides taking a lot of thermal energy to make the temperature increase, it also takes, or would have to lose, a lot of thermal energy to make the temperature decrease. Or another way to say that is it takes a lot of heat for it to it heats up slowly because it takes a lot of thermal energy to make the temperature actually go up, and it also cools down slowly because it has to lose a lot of thermal energy for its temperature to change. Water is a good example. Water has a high specific heat, and so it takes a lot of thermal energy to warm it up, and it would have to lose a lot to cool down. So it heats up slowly and cools down slowly. On the other hand, metal has a low specific heat. Low specific heat means it takes relatively little thermal energy to make the temperature go up, and it could lose, it only has to lose a little thermal energy to make the temperature go down. So in other words, things with a low specific heat, the temperature will rise very quickly with even a little heat added, like a metal. That's why I use them for pans and stuff like that to cook with, because a little thermal energy makes them heat up quickly, and then also if you take them off the heat, they will tend to cool off fairly quickly. All right, so that's part about the specific heat, and that will help you with the first couple of questions as well as the rest of the chapter. Now let's look at the chart, or question number 3 there, basically. On this you have a chart, and it says you have some objects. The object that you're talking about for each question is the words in bold print. So for example, ice cube is in bold print. So for the first question, you're going to answer, put an answer in each blank based on the ice cube. And the first question is, if you put the ice cube into a glass of room temperature lemonade, is the ice cube gaining or losing heat? All right. Well, we know heat goes from high temperature to colder temperature. So which one has a higher temperature, the room temperature lemonade or the ice cube? Very good. The answer is the lemonade. So it's going to go from lemonade into the ice cube, and therefore the ice cube is going to gain heat, or gains heat. So if you want to put gain or gains in that first box where it asks is heat is gained or lost. Now, the next question asks you, is it endothermic or exothermic? Endo means it's taking in heat, and exo, like exit, means going out or leaving, so it is going to get rid of heat or give off heat. All right, so the question in this case is for the ice cube, is it gaining, taking in heat, or is it losing heat or giving off heat? In this case, it is taking it in. So the correct answer would be endothermic, and you can just put endo in the blank there. Unless you have small handwriting, you can go ahead and write the whole endothermic part. Now, the last question has to do with Q. Q is the amount of heat energy that's either gained or lost. If you gain energy, if you gain Q, then it's going to be a positive number. If you lose heat energy, or Q, it's going to be a negative number. In this case, we said the ice cube is gaining heat, so it would be positive. Okay, then you would just do that for the rest of it. You have a lemonade just sitting outside on a hot day. So you're saving for the glass lemonade, the burners on the stove, the dry ice, and finally the water vapor down at the bottom. Okay, so for each of those, fill out, is it gaining or losing energy? Is it endo or exothermic? And is X positive or is X negative? All right, now the next questions are going to have to do with the Q formula. The formula for Q is Q equals mass times the change in temperature, which is the final temperature minus the initial temperature. You could say that's delta T, but that's basically final minus initial, times the specific heat. Okay, so if we want to find Q, that's what we would have to do. All right. Now, so look at number 4 down at the bottom. We have a sample of zinc that was heated up on a hot plate. We'll put that off the screen somewhere because I can't draw a hot plate. And we put that piece of zinc into a cup full of water. And that would be that right there. We'll put a ZN on it. That's kind of hard to read. But anyhow, that's our piece of zinc. Okay, we had heated it up, and then we put it in the water. Now, when we put it in the water, where's heat going to go? Well, the zinc is hotter, so it's going to go from the zinc into the water until they reach the same temperature. Is that right? Because we know that heat always flows from high to low until both become the same. So, the first question it wants to know is, what is Q for the water? I'm going to put QH2O down here just to say it's Q for the water. That's what we need to know. All right. So first thing we need to know is the mass of the water. Well, it tells us we have 50.0 milliliters of water. Unfortunately, milliliters is not mass. Grams is mass. But it just happens, if you look in the parentheses there, it says the density of water is 1 gram per milliliter. So if we have 50 milliliters of water, guess how many grams we have? That's right, 50 grams. So 50.0 grams of water would be the mass. All right. Then it says the water was at room temperature, which was 27.0 degrees Celsius. All right. And it warmed up to 28.1 degrees Celsius. Notice it didn't warm up very much, but that's because water has a high specific heat. All right. So now we're ready to plug into our equation, except we need to know which one of these is the initial temperature and which one is the final temperature. So we know that 27.0, that was what it was before we put the zinc in, so that's going to be our initial temperature, and the final temperature is going to be after the zinc was in it when it warmed up to 28.1. So to put in the formula for Q, Q is equal to the mass, which is 50.0 grams, times the final temperature, which is 28.1 degrees Celsius, minus the initial temperature, 27.0 degrees Celsius, times the specific heat of water. All right. If you look on the back, there's a chart that gives you the specific heat of some different substances, and at the very bottom is water, and water is 4.186 joules per gram times degrees Celsius. Okay, so that's pretty much that. Unit-wise, we have grams over here, and we have grams on the bottom of a fraction over here. They are going to cancel. And here we're going to have degrees Celsius, and they're going to cancel with this degrees Celsius down here. So our units are going to be joules. That's the only thing left, and that makes sense because Q is thermal energy. So we do 50 times, if you subtract these two, you get 1.1 degrees Celsius. All right, times 4.1. And that should give you a little over 200. In fact, that gives you about 230.23 joules. Okay? Now, if we went back and looked at SIGDIGs, if you just looked at the SIGDIGs of the numbers, the measurements we had here, they all had 3. All right? But if you subtracted this, since you're subtracting, you look at the number of decimal places. They each had 1 decimal place, so your answer should have 1 decimal place. That means this only has 2 SIGDIGs. So if we round this to 2 SIGDIGs, it would just be 230 joules. All right. Now, if you did it from these and said there should be 3 SIGDIGs, just for the record, you should have 2.30 times 10 squared joules, which is the same thing. It just changes the number of SIGDIGs, but either one would be fine on that one. All right. So we know that the water would have gained 230 joules of thermal energy. Now, on the back of number 4, the second part of number 4, this time we're talking about the zinc. This is important, okay, because now we're not talking about the water anymore. Now it's going to be the Q value for zinc, it's going to be the mass of the zinc, it's going to be the final initial temperature of zinc, and eventually we're going to try to find what the specific heat of zinc would be. All right. Now, first thing, if we want to do Q for zinc this time, all right, we know when we put the zinc in the water gained 230 joules. We said that last time. We said that the water gained 230 joules. Well, the zinc cooled down, so it lost energy. And how much energy did it lose? Guess what? 230 joules. But because it lost it, it's going to be negative 230 joules, because it lost the amount of heat energy that the water gained. All right, so Q is that. All right, then you'll have to go through the problem. It gives you the initial temperature of zinc, it gives you the mass of zinc, and then you can plug in the formula and solve for CP. Now, the only thing is, the first question says, what is the final temperature of the zinc? Well, how do I know that? Remember, we put the zinc in the water and the heat went out of the zinc into the water until they were both the same. So we know that the final temperature of zinc is the same as it was for the water, which is 28.1 degrees Celsius. All right, so the first question, the final temperature of zinc, no calculations, just logically thinking about it, it's going to be the same temperature as the water, and it's going to be the 28.1 degrees Celsius. All right, the rest of the information is in the problem, and you can use that to solve for the CP, or specific heat of zinc. All right, now that formula will also be good for number 7 and 8. For numbers 7 and 8, you will be finding Q. Okay. For gold, notice you will need a little chart there that gives you the specific heat for gold right above that. Okay, and also for number 8, number 7 is going to be for water, which gives you the specific heat up there, and number 8 is for gold. But either way, you're finding Q on that one. Number 9 is the same formula, but this time you're solving for the mass of the aluminum. All right, so you can find the Q, the final initial temperature, the specific heat is on the chart, and then you can calculate what the mass would have had to have been if you solved for M. Number 10 is going to be kind of like a bonus, okay? No, that doesn't mean you don't have to do it. That means you have to do it, but if you get it right, you're going to get extra credit. In this case, you're trying to find the final temperature of water, okay? And so you're trying to find the final temperature right there, which you can do using that same formula. Now, the only questions that we haven't talked about are number 5 and 6. 5 is similar to the chart. It describes what happens to an object, and then you'll put positive or negative depending on whether it gained thermal energy or lost thermal energy. Then on number 6, they give you two substances, and they want to know that if you apply 1,000 joules of heat to either one, same amount of heat to both of them, which one's temperature will go up. And that goes back to what we talked about, specific heat. Think with a high specific heat, their temperature goes up slowly. If think with a low specific heat, their temperature goes up quickly. So between those two, you should be able to figure out which ones. Enjoy.